Alright, welcome back. Today we're just going to go through Chapter 2, which the point of Chapter 2 is to lay a couple more groundwork, aka framework here, of what testing is, and to also get a couple of terms straight in our minds when we go towards talking about testing. It's also going to give a brief overview of generally how people think of testing when they approach it from a business perspective. Alright. A couple learning objectives, that's fine. The big thing we need to figure out first or understand is the difference between validation and verification. The validation is done by the users. It's are we building the right software? Basically, are we actually doing what the user or the customer is asking us to do? Did we build it correctly? Verification is a little different. It's did we design it? Did we write it such that it met our specifications? Keep in mind that the customer is going to tell us, hey, look, we want you to do this piece of software. We want to write a web page that does blah, blah, blah. And then we are going to, as engineers, come up with a design specification that we believe meets those requirements. Now, you have to understand that these are two different things. What the user wants and our design specifications are rarely perfectly aligned, but the idea is that you want to align them as much as possible. And when you go to verify your software, you're verifying against your own specifications. When you go to validate it, you're validating against the user's expectations of the software. Hopefully that gets validation and verification straight. Here's another picture. Same thing I was talking about, actual requirements. I like the cloud because it usually is kind of amorphous what exactly the customer wants. You just have to sit down and try your best. A lot of companies will actually have one person whose whole job is to get these actual requirements and then come up with some type of specification. It's probably a really tough job, and I don't think I'd want to do it, but it is very important. And then your verification is actually you get your specs and you write the system, you verify it meets it, and then the validations when you step back and you say, okay, the system that we have hopefully verified, does it actually meet the user's requirements? So everything depends on the specification. There's unverifiable but validable, aka something you can validate but you can't verify spec, and then there's actually something you can verify. The point of this is that something you verify is usually very concrete, and it's usually with numbers, it's quantitative. We can actually set up a system, test it, and make sure it responds. While something verifiable is, validable, but but you can't verify it. Man, that's a tongue twister. Is something that the user will just say it works or not. For example, you have the elevator. The user just wants to press a button and go to a floor, and they want to do it must arrive soon. Well, what defines soon? Well, that's relative based on different users. So the fact that it says soon, and it's not something that's been quantitative, it's actually a qualitative attribute, makes it unverifiable. But you can still validate it because humans can validate qualitative attributes. Verifiable would be the same thing, but the elevator must move within 30 seconds. Okay, we can verify that because we can actually set up some mechanism to time when the elevator moves from one to another. So hopefully that makes it clear what something's verifiable and unverifiable. But keep in mind that both of them can still be validated. When you go through the software engineering process, hopefully you've done something similar to this before, but if not, usually the way this works is there's the actual needs and constraints from the user. If you have someone good, they can come and translate that into that system specification I was talking about earlier. And then afterwards, you may break that down into different sub systems or different sub specs. Usually there's you're not going to have one giant document. You're going to probably have something for each subsystem. And then even in each subsystem, you'll probably break it down into units. Keep in mind that this could be for very small projects, one box. But you could also, for medium size, probably 3 boxes, and for really, really large, it might be broken down a lot. But the point here is you keep breaking it down until you have smaller chunks, and this is very common, divide and conquer. And then usually your unit component testing or verification will verify the units, and then maybe you'll go up, all right, we have verified the units, let's see if we paste them together, the subsystems together, do they work? Okay, we'll verify the subsystems. All right, let's put it all together and see if we can verify that the system's correct. All right, we can verify the system. Now we can deliver the package, and you have something called user acceptance testing, or you're now going to go in and actually validate. what's going on. So you can't always get what you want. Yep. Correctness properties are undecidable. Hopefully after viewing the halting problem, you can see that just even simple correctness, hey, does this program not fail, not go in an infinite loop, is something we can't even decide. The big trick here is the halting problem can be embedded in almost every property of interest. It really, once your program becomes large, it's not just the whole problem or program that has the halting problem. Even subsystems or even units of code will have the same issue, and so proving correctness is just something that's simply undecidable at this time. All right, a couple more terms. Probably not used to these three if you've been working, but that's okay. We're going to go ahead and run through them real quick. So optimistic inaccuracy is accepting programs that do not possess a property. So it may not detect all violations. So this is very common in testing, where you will detect maybe some of them, but you'll have an optimistic inaccuracy where you'll not be able to detect all of them. Pessimistic inaccuracy is not guaranteed to accept the program even if it does possess a property being analyzed. So this is kind of in the reverse, but the way you have to think about it is pessimistic inaccuracy means that you're going to have some false negatives, so to speak. It's going to say, yeah, this one didn't work, when in actuality it did. Testing, on the other hand, would have false positives because you're saying, well, it passed all our test cases, it must be good. Oh, wait, we didn't test for something else. Hopefully those two make sense. If you prefer using false positive and false negative, I'm perfectly fine with that. I think that actually makes a little more sense to a business perspective, but the book is going to use optimistic inaccuracy and pessimistic inaccuracy, so please just keep that in mind. Simplified property, this is very common, very good thing to do to reduce the degree of freedom for checking something similar. And I believe we give a nice, great example here of the simplified property, aka they call it the simplified property. It's just simplification. On the left is something that's complicated, and on the right it's been simplified. And this is very common in Java. If in C, or even in Java in some cases, you may need to lock and then unlock something, maybe inside using mutexes. This is a very common example. On the left, it's complicated because you may lock it and then you have code and then you hope the unlock actually gets called, but you have to really do a lot of static checking and maybe even some runtime checking to guarantee that, hey, look, we actually unlocked it at the right time. On the other hand, Java says we're going to synchronize this on some mutex, open curly bracket, close curly bracket, and it's just saying that, all right, once we go in here, you have grabbed the lock, and once you're out of this curly bracket, we are now unlocked. So this is something by building it into the language, it's easier to test. You have simplified the problem from trying to do the static analysis to synchronize. Now remember, this is just an example. There's other ways to simplify your testing. So you do want to go towards languages, or I guess tools really, that can simplify what's going on. Obviously, if you're in C, you could come up with a simple library that would increment or create something like synchronized on the right, and that would probably be a wise decision because then you could just test that library functionality and then move on from there. All right, more terminology, just got to get this all out. Safe has no optimistic inaccuracy, so it only accepts correct programs. In other words, there's no false positives. Sound. All right, that one's kind of complicated, but analysis of program P respect to formula F is sound when the analysis returns true only when the program satisfies the formula. So only and satisfies the formula. So you know on the certain inputs it's going to work correctly. And complete an analysis program P with respect to formula F is complete if the analysis always returns true when the program actually does satisfy the formula. So sound means it's going to work on some. F is going to always return true for all inputs. All right. So a couple things we learned important here. We got a bunch of terminology out there. We optimistic inaccuracy, pessimistic inaccuracy, safe, sound, complete, and the other. Let's see. Other thing to keep in mind is that we're using. Is again, the halting problem has essentially made it so that we cannot just automate these tests. We can't guarantee correctness. All we can do is increase our confidence that your program is correct. And I think that's the best way to think about it or look at it from a testing perspective, is what level of confidence do you want? And if they ask for 100%, you just have to unfortunately tell them it's just not possible. But if you want 99.9999, okay, we can work with that. All right, that's it for this presentation.